Welcome to Physics with Joe. In my last video, I talked all about equations of constant acceleration in one dimension, either horizontal or vertical. What we went through was what are the different quantities, the different physical quantities that you always see when doing problems with constant acceleration, things like initial and final position, initial and final velocity, and so on. We looked at what are the four equations of constant acceleration, and then I gave you a simple problem-solving strategy that you can use for most constant acceleration problems. If you haven't seen that video yet, I highly recommend you watch that first. I will put a link in the description below. Today I want to do a short video talking about a slightly more challenging example problem where the acceleration changes midway between the problem. Meaning I have a certain constant acceleration for one part of the problem, but then the acceleration changes to a different value for the second part of the problem. Can I solve that problem in one step, or do I need to use multiple steps? Without further ado, let's jump right into it. Before we do this example problem, let me just remind you of a simple problem-solving strategy you can use for almost any constant acceleration problem. Step 1, read the problem and visualize what is happening. Do not just start taking numbers from the problem and trying to find an equation to use in the book, plugging them in without thinking about it. Take the time to read the problem, think about what the problem is describing and what it's asking for. If you need, draw a diagram, draw a sketch, but really take the time to read the problem and think about what's going on. Step 2, identify the known and unknown quantities. There's always 6 different quantities that you'll see in any constant acceleration problem. Initial and final position, initial and final velocity, acceleration, and elapsed time. In this step, what you're doing is reading the problem, figuring out what we're given and what we're looking for, getting the known and unknown quantities. Step 3, find the equation that has your unknown quantity and known quantities. And I'll give you an easy way of doing this. Step 4 is then solve algebraically for the unknown quantity. Do not start plugging in numbers. That's a really bad habit to do. You want to do that as your very last step. So first solve algebraically for the unknown quantity. Then step 5 is actually plugging in the known values to get your unknown quantity. And then step 6 is just making sure your final answer seems reasonable. Does the magnitude of your answer make sense? Do you have the correct sign? Do the units work out? And that's really all there is. Quite simple. Read the problem, visualize what's happening, identify your known and unknown quantities, find the equation that has your unknown quantity and known quantities, solve algebraically first for the unknown quantity, finally plug in your known values to get your final answer, and then make sure that answer seems reasonable. I think the easiest way of identifying the known and unknown quantities and finding which equation has your known quantity and unknown quantities is by using a simple table. Now, as you see here, I've got on the left-hand side all of the equations listed, and then next to each equation, I have the 6 different variables, the 6 different quantities, and which quantities are contained in each equation. For example, Vx equals V naught x plus Ax delta t. I have my initial and final velocities, I have my acceleration, and I have my elapsed time. I do not have my initial or final positions, which means I could not use this equation to solve for x or x naught. Then below this table, I also have listed the 6 physical quantities that you always see. You can then use this to put your unknown quantities and known quantities into it, and then by using the table, you can see pretty easily which equation contains your unknown quantity as well as your known quantities. Well, let's do this example problem and see how to put this into practice. Okay, let's take a look at this example problem, which states the following. Starting from rest, a speedboat accelerates at plus 10.5 meters per second squared for a distance of 525 meters. The engine is then turned off and the speedboat slows down at a rate of -5 meters per second squared until coming to rest. How long is the speedboat in motion from start to finish? Well, let me ask you a question to start off with. Is it possible to combine the two different accelerations, the plus 10.5 meters per second squared and negative 5 meters per second squared, into some kind of average acceleration and do this problem in one step? And the simple answer is no. If the acceleration changes, then that in essence is like a whole nother problem. You have to do these in pieces. Part 1 is going to be when the speedboat starts from rest, accelerates at 10.5 meters per second squared for 525 meters, and then part 2 is going to be when it accelerates at negative 5 meters per second squared until coming to rest. Since the acceleration is different in each part, I have to treat each one separately. Well, let's start with part 1. Part 1 is going to be when the boat starts from rest and accelerates at 10.5 meters per second squared for 525 meters. Well, starting from rest. Ding, 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 ding. Anytime you hear that phrase, you know that the initial velocity is going to be 0 meters per second. We know the acceleration, and we know it accelerated over a distance of 525 meters. Now, I can define my origin wherever I want. And oftentimes it's easiest to define x equals 0, the origin, as where the object starts. And that's what I'm going to do here. I'm going to let the initial position be x naught equals 0 meters, in which case my final position is 525 meters. So let's write down our known and unknown quantities. We know that the object started from rest. It accelerated at plus 10.5 meters per second squared. The initial position was 0 meters. The final position is 525 meters. I do not know my final velocity, and I do not know my elapsed time. Now, I'm definitely going to need the elapsed time in order to get the total time from start to finish. But do I need the final velocity at the end of 525 meters? The answer is yes, because in the second part, now whatever that velocity was at the end of 525 meters, that's going to be our initial velocity for part 2, where it starts at that velocity and then slows down until coming to rest. So I'm going to need both Vx and delta t. Well, if you look, I have initial position, final position, initial velocity, and acceleration. I'm looking for my final velocity, and I'm looking for my elapsed time. Well, let's start off by getting the final velocity. So I have x naught x, v naught x, ax, and I'm looking for vx. Well, if you look, all of these quantities, the known and unknown, are contained in this equation, vx squared equals v naught x squared plus 2ax, x minus x naught. So I'm going to use that to get my final velocity. So I'm going to write this equation to start with. Vx squared equals v naught x squared plus 2ax, x minus x naught. Now we want to solve algebraically for the unknown quantity. My preference is to plug in any values that are 0 first, just to make the algebra a little bit easier. So we know the initial velocity was 0. We defined our initial position to be 0. So this equation reduces to vx squared equals 2ax times my final position x. Take square roots of both sides and you get vx equals plus or minus the square root of 2 times the acceleration times the final position. Remember, anytime you're taking the square root, you always get a plus or minus. In this case, we're assuming all the motion is to the right, so I'm going to choose my positive square root for the velocity. So my velocity then is plus the square root of 2 times 10.5 meters per second squared times 525 meters. Plug that into your calculator, and what you're going to get is your final velocity is 105 meters per second. Pretty fast, over 200 miles an hour, but speedboats can definitely reach that speed. So now we know our final velocity is 105 meters per second. Now we want to know what is the elapsed time. how long did it take to reach that final velocity? Well, if you look, I could use this top equation to solve for delta t. I could use this second equation to solve for delta t, or I could use this last equation to solve for delta t. Well, I'm just going to choose the first one because it's the easiest. We have Vx equals V naught x plus Ax times delta t. Again, plug in anything that's 0. We started from rest. So this equation reduces to Vx equals Ax times delta t. I can solve for my time delta t equals Vx divided by Ax, plug in my values, and what I get is 105 meters per second divided by 10.5 meters per second squared. What I get for my time, my elapsed time, is 10 seconds. So at the end of 525 meters of accelerating at 10.5 meters per second squared, the speedboat is now going 105 meters per second, and it took a total of 10 seconds. Now in part 2, the boat's initially moving at 105 meters per second. It's slowing down at -5 meters per second squared until it comes to rest. And we want to know how long does it take to come to rest so we can get the total time from start to finish. The time for part 1 was 10 seconds, so we just need to find the time for part 2. Again, we've got our handy table with our list of known and unknown quantities. In this case, the initial velocity is 105 meters per second. The acceleration is -5 meters per second squared. The speedboat ends up at rest, so my final velocity is 0 meters per second, and I'm looking for my time. So I've got V naught x, I've got Vx, I've got Ax, and I'm looking for delta t. The one equation that has our unknown quantity plus known quantities is Vx equals V naught x plus Axt. So for part 2, what I have is my equation Vx equals V naught x plus Ax delta t. We end up at rest, so our final velocity is 0. So this reduces to 0 equals V naught x plus Ax times delta t. Solve for my elapsed time, and what I get is delta t is -V naught x divided by Ax. Put in my values, and I get my delta t is -105 meters per second squared. Sorry, meters per second divided by a -5 meters per second squared. And what I get is my time, my elapsed time for part 2 is 21 seconds. So we wanted to know what is the total time from start to finish. So my total elapsed time is going to be my time for the first part, which is 10 seconds, plus my time for the second part, which is 21 seconds. So my total elapsed time from start to finish is 31 seconds. Well, that is it for this example problem. Well, that is it for today's episode of Physics with Joe. My name is Joe McCullough, and thank you so much for joining me. In my next video, I'm going to be talking about free fall. So until then, that's it. See you next time.